What are the essential diesel cycle formulas for work and heat transfer? Imagine a process where fuel energy is transformed into motion inside an engine. That's what the diesel cycle does, powering many trucks and heavy machinery. Today, we'll uncover the key formulas that explain how work and heat transfer happen in this cycle. The diesel cycle involves four main steps. First is the isentropic compression, where the air is squeezed tightly, raising its temperature and pressure without losing energy. Next is the constant pressure heat addition, where fuel burns at a steady pressure, adding energy to the system. Then comes the isentropic expansion, where the high-pressure gases push the piston down, creating useful work. Finally, the cycle ends with constant volume heat rejection, where leftover heat escapes as the gases cool at a fixed volume. To understand the work and heat transfer, we focus on the formulas for heat added and rejected. The heat added during the constant pressure process from state 2 to 3 is calculated by subtracting the enthalpy at state 2 from that at state 3. This is written as Q23 is equal to H3H2. Enthalpy combines internal energy and flow work, so it tells us how much energy is added during fuel combustion. The heat rejected during the constant volume process from state 4 to 1 is found by subtracting the internal energy at state 4 from that at state 1, expressed as Q41 is equal to U1U4. Internal energy reflects the energy stored in the gases, which decreases as heat leaves the system. The net work output of the cycle is the sum of the heat added and rejected, which simplifies to the difference between the enthalpy change during heat addition and the internal energy change during heat rejection. Mathematically, its W net is equal to Q23 plus Q41 is equal to H3H2, U for U1. This network shows how much energy is converted into mechanical motion per unit of fuel burned. The work done during compression and expansion can be estimated using pressure-volume relations, assuming the gases behave like ideal gases. These calculations often combine into the net work formula but are useful for detailed analysis. The efficiency of the diesel cycle depends on the compression ratio, which is how much the air is squeezed, the cutoff ratio, which relates to how much the fuel is burned during the constant pressure process, and the specific heat ratio, which compares the heat capacities of the gases. The efficiency formula looks like this. Plus eta is equal to 1 plus times plus frac RCK1K RC1. Higher compression ratios and cutoff ratios generally improve efficiency, meaning more work is gained from each unit of fuel. Remember, enthalpy combines internal energy and flow work, while internal energy is the energy stored in the gases related to temperature. The difference in these properties during each process helps us understand how energy flows and how much work the engine can produce. These formulas are essential for engineers designing diesel engines, helping optimize performance and fuel use. They show how energy input during fuel combustion translates into mechanical work and how heat is transferred during each step. By understanding these principles, we can improve engine efficiency and reduce fuel consumption, making diesel engines more effective and economical. So, the core formulas for work and heat transfer in the diesel cycle revolve around changes in enthalpy and internal energy during constant pressure and constant volume processes. The net work output depends on these energy changes, and the efficiency links these processes to engine design parameters like compression and cutoff ratios.